I will try to give you an introduction to homotopy in algebraic geometry. So to do that, I will have two parts. In the first part, I will recall some basic facts from standard algebraic topology. So standard algebraic topology. In standard algebraic topology, you are always led to study the homotopy category of CW complexes. So the basic object, the homotopy category, we call it briefly. So as object, we have CW complexes, which are, well, topological spaces which emits a kind of triangulation in some sense, kind of cellular triangulation. Such as manifolds, for example. Okay? And morphism, just homotopy classes of maps. Continuous maps. So this is the basic object of study in algebraic topology, and one tries to understand it by defining functors. So I will give a name to this category, H. So one tries to define functor from this homotopy category to more algebraic categories, such as abelian groups or more sophisticated invariants, in order to study this homotopy category. So the most basic construction is the following: singular homology construction the singular chain complex, so which assign to, well, in fact, any topological space a complex of a abelian group, which is defined in the usual way, and whose homology group are the singular homology of X with integral coefficients. And this construction defines a functor from H to the derived category of abelian groups. So, well, this is, in some sense, the homotopy category of a complex of abelian groups. So you invert in that category of complex of abelian groups any morphism which induces isomorphism on homology groups. Okay. So this is a very basic construction. So of course it is well known that this construction, this functor, loses much information from that category. Okay. So you cannot reconstruct, of course, a topological space to homotopy by only considering this its image here, which is only the singular chain complex. So I will give you the most naive example. If you take the following two spaces, complex projective space, P2 of C, and the wedge of the 2 sphere and the 4 sphere. Okay, wedge means that you take the union of these two topological spaces along one point. Okay, and these two spaces have the same image here. Their chain complex are homotopy equivalent. So of course, these spaces are not homotopy equivalent. So how can we prove this? What do you have to use to distinguish these two spaces? Then you can do that is not isomorphic to this one in the homotopy category by looking at the multiplicative structure on cohomology, for example. And I will take on mod 2, singular cohomology. Okay, this is a general fact. Singular cohomology with coefficient in a ring has a structure, a natural structure of rings, graded rings. And just check that the two mod 2 cohomology of these two spaces with their ring structure are not isomorphic. And how do you do that? Cohomology of P2 is just truncated polynomial algebra over a class of degree 2 divided by U3 equals 0 as a ring, as graded. In particular, so this is the class here, which is non-zero. In fact, there is only one non-zero class, such that U square is non-zero. And for this space, this property is not true. Okay? So the structure, the multiplicative structure in some sense is trivial, and any product is zero. So what we use to differentiate these two spaces is only the map from H2 to H4, in fact, which does exist for any space, which is given by the cut product of the class by itself. And this map is a linear map, a natural transformation. So now we have an example of cohomological operation, which shows you that it might be used to distinguish two spaces up to homotopy. So it doesn't that this kind of cohomological operation are very very rich structure on to cohomology. I will just recall you the basic theorem on the existence of Steenrod square, which this map is a particular case, and we'll give you a more sophisticated example like this one. So the basic theorem about Steenrod operation is the following. There is a unit collection Qi, index n, indexed by pairs of integers, so n positive, I is positive, of natural transformation from where to where, from between functor from H to category of abelian groups. So from So these are natural transformation of functor to abelian groups from nth singular cohomology group with mod 2 coefficient to hn plus I. Okay. So this is skew I n, and this equal. Usually the n will be dropped. Okay. Should only denote this transformation by skew I, and with the following properties. First, for any n, skew naught is the identity for any class U, for any cohomology class U of degree n, skew in of U is 0 if I is strictly more than n, and is the square, U square, if I is n. And finally, the Cartan formula which say that skew I n of U cap V, where U is a class n plus n. U is a class of degree n and V of degree m, and this is the sum of j plus k equal I of skew j n U cap skew k m V. So you have characterized the Steenrod operations, and the notation square comes obviously from this property. You have only one way to extend this operation, which we use here, in this way. No, it is implied by the Cartan formula. If you apply the Cartan formula for, yeah, you get the suspension. So, sorry? Yes, usually it is stated as saying that it is a stable operation, but it is implied by the Cartan formula. So, as a consequence, yeah, as a consequence, you can show that the skews are linear operation, for example, are additive, and so on. So, but I mean, this is the uniqueness result, so you can prove everything you want, which is true. So let me make some remarks. It can be shown that skew1 is the Bochstein expression from hn to hn plus 1. Also, it is well known that the skews have rather non-trivial relation between them. So for any pair of integer a, b, so with a strictly less than 2b, one has the following relations. Skew a composed with skew b is a sum over c, a binomial coefficient, like that. And this has the formal consequence that if one defines A, the Steenrod algebra, to be the quotient of the tensor algebra, tensor graded algebra over generators skew I of degree I by the Adam relations, then formally for any spaces the modulo 2 singular cohomology as a natural structure of left A module. So this structure is quite rich, as it was first pointed out by Adams, constructing this spectral sequence, which computes some homotopy groups and starts only from a little term, which involves only this kind of structure. And the structure of the mode 2 cohomology of spaces is shown to be very powerful in standard algebraic topology. I don't have time to explain why, but let me mention the following topics concerning the Seagal conjecture and the Sullivan conjecture. I don't have time to give you more about that. So now I will go back to my first example, and we'll show you how this kind of consideration can give strong homotopy information in a very simple way. And this will close my recollection on standard algebraic topology. Of course, I have not covered everything, but I try to give you some information which are needed to understand what Voevodsky uses in his work. So now the concluding example is the following. Lemma, let X be a space, topological space, and assume that its mode 2 cohomology and the graded ring is a truncated polynomial algebra of this type with U class of degree n. Then n is the power of 2. So you can't easily prove this lemma without using Steenrod operation. It's very easy to deduce it from here. The proof is that the Adam relations imply that any operation sqn with n not a power of 2 are decomposable, which means it can be written as sum of qi, qj with both I and j different from 0. Okay? And now you apply this to U, and if n is not power of 2, then sqn n is this one, the degree of U. Okay, so you apply sqn of U. So you know on one hand that is the square, U square, which is assumed to be non-zero here. But now you apply this formula, you get a sum of decomposable elements. And of course, j is strictly less than n. So this class qj of U is 0. And all the sum vanishes. So you have a contradiction. So n must be a power of 2. So this is basic and the more elementary example of what the structure of module of a Steenrod algebra can give you. Of course, we know that Adams has proven that in fact n must be 1, 2, 4, or 8. But this is more complicated and involves either it's Adams spectral sequence or K-theory, which are related. Okay, so this closes my recollection. and standard algebraic topology. So now I would like to introduce you to algebraic topology or homotopy theory in algebraic geometry. So the recent work of Vladimir Voivodsky and his collaborators has shown the following. For any field K, one has the following picture. Well, very often I will assume that characteristic is zero, to have the resolution of singularities and to have the basic property of motivic homology. So one has the following picture, which is absolutely analogous to this one. One has a category, H of K, which we call the homotopy category of smooth variety over K. So one has a functor which looks like the singular chain complex functor, which is usually denoted like that, but which can also be denoted like that, M for motives, which goes from the homotopy category to a triangulated category, which Voivodsky calls a triangulated category of mixed motives. Over K. So in some sense, this is the analog of the homotopy category of CW complexes. The functor of associating motives is the analog of the singular chain complex, and this category is the analog over K of the DRF category of Fabien groups. Well, let me just mention that if you assume K as characteristic 0, this category contains as a full subcategory the category of effective Schau motives with integral coefficient, which may be a motivation for calling this triangulated category, the triangulated category of mixed motives. So this concerns only projective smooth varieties. And the analog of singular cohomology, of course, is motivic homology for smooth varieties, which I will denote like that. So now in algebraic geometry, it is bigraded because in some sense the coefficient z of 1 is a twisted system. So you can tensor it anytime you want, and you get something bigraded. So I don't have time to define it, but I guess that Vladimir will say you more about this category, and maybe this one in his talks. And the analog of singular homology is Sussin homology, which can be easily defined very easily. So now what happens? So what can we do with that thing? So what is absolutely fascinating is that to prove the Milnor conjecture, you do need this, to have this picture in mind. And you have to really to have this picture in mind. So I will try to, not of course to explain you the proof of the Milnor conjecture, but to sketch you the proof of the crucial homotopy part of proof of Milnor conjecture, and try to explain you why it deals with Steenrod operation, for example. Well, I could maybe mention that, contrary to the case of standard algebraic topology, H of K is not the naive homotopy category you could imagine by just taking. This is a remark. HK is not define is object smooth varieties, and as morphism, the set of algebraic homotopy classes from x to y, where x and y are smooth varieties, and it is a quotient of the set of morphism of smooth varieties from x to y by the equivalence relation generated by elementary algebraic homotopy. So let's say that two morphisms from x to y are elementary algebraically homotopy equivalent if there is a homotopy from x cross the affine line to y, which satisfies the obvious condition that the morphism from x to y induced by the 0 section is f, by the 1 section here is g. So this is not an equivalence relation, so you have to take the equivalence relation generated. So the homotopy category, unfortunately, is not this one. It is a little bit more complicated to define, but certainly you have one as a functor from this naive, which I will call like that. This naive homotopy category to the true one. Okay, so this can be a first approximation. This one? No. Almost. I mean, this category is the localization of the category of simplicial smooth varieties. If you allow a smooth variety to be disjoint union of any family of smooth varieties, I mean, you can have an infinite set of connected components. So this is another remark. This functor extends as a function from the category of simplicial objects in that category. So delta up smooth came in simplicial object to this one, and these are constant simplicial smooth varieties. So in some sense, you can also define the motivic homology of simplicial smooth varieties. Motivic homology only depends of a simplicial smooth variety only depends on its motive. So you look at it in that category, you take the functor of motive, you are in the triangulated category of effective mixed motive, and you can define there its motivic homology. Now, Vygotsky is here to study the following kind of objects, which are very well known in topology. Let X be a smooth variety, okay. Let introduce a simplicial smooth variety, C check of X, as follows. So it is a functor from the category delta up to the category of smooth variety. So I must give you for any integer n a smooth variety, and you take the product of x n plus 1 times by itself over k, over spec k, and faces, which are morphism from each lower the degree, are induced by projection and degeneracies, which rises the degree by diagonal. So this kind of object is, this is a remark, in standard topology, the homotopy type of this object in the homotopy category of CW complex is easily computed. It is equivalent to the point if X is non-empty, and it is the empty space if X is empty. So the reason is that to have a homotopy to the base point here, you need to choose a point in X. Of course, you cannot do that if X is empty. This is, well, this is quite trivial here, but this is very important in... Sorry? Yes, but you can realize it. Yeah, it passes this kind of thing. So now in algebraic geometry, these objects are much more certain. Objects like this are much more certain. And the crucial lemma, Voevodsky, the crucial theorem of homotopy nature, Voevodsky involves this kind of objects with no rational point. If X has no rational point over K, which is the analog of being non-empty in topology, to have a point here in algebraic geometry exactly means to have a rational point over K. So if X has no rational point over K, you cannot say much. Okay? If it has a rational point, then this is contractible in HK. If it does not, then you cannot say much. And his main theorem does say something about motive ecology of this kind of objects. So to say something, Voevodsky constructs cohomology operations on motive ecology with the mode 2 coefficients, which are now bigraded objects. More geometrical. You have to, well, the general spirit here is that any construction in algebraic topology can be made, which is reasonable, can be made algebraic. But you have to think about, I mean... Yeah? Yes, but here you need some geometrical input. I mean, you need to know what is the Thom class of vector bundles. And this is not completely, yes, homological algebra. I mean, there is something more, which is not completely clear. You do need to construct this Steenrod squares.
More the right edge.
Yes, I mean, yeah. You need more to just read the book and understand it. Okay, but basically it is it gives the same construction essentially. So for each eyes, you have a cohomological operation of these guys of by degree. So I and integral part of I mod 2. Okay, and of course, SQ1, SQ0 is the identity. SQ1 is the Box-Stein, which is associated to a long exact sequence in motive ecology with respect to the exact sequence Z mod 2, Z mod 4, Z mod 2. But of course, even to prove this is not completely formal. You have the same problem as in topology to prove, for example, that you have no Steenrod square for I negative. And here you have to use resolution of singularities to have some bounds on the cohomology of the representation of the Zellner-Maclaurin spaces, which classifies the motive ecology. So this is not completely formal. So this is yeah.
C as what is beta?
Beta is Bochstein. And it just rises the cohomological degree by 1 and do not touch the twist. Here you have pi degree 1, 0. Okay, and this is the usual Bochstein associated to the exact sequence Z mod 2, Z mod 4, Z mod 2. So now it proves that this Steenrod operation satisfies some relations which are analogous to Arden's relation but a little bit more complicated, which anyway allowing to prove the following things. For any positive integer defines inductively an operation qi by qi equal to the Bochstein if I equals 0 and equal to the commutator between the previous operation and skew Steenrod square of degree 2 to the I. This is the commutator of two cohomological operations. So the relation satisfied by the QIs allows me to prove that the QIs are derivations. So if you compose QIs by itself, you always get 0, as for the Bochstein. And as in topology. Of course, you can do the same thing in standard algebraic topology, and it is well known that this is 0. These are called the Milnor elements in the Steenrod algebra. So now I can state his main homotopical theorem. I do not have the time to explain why he does need this theorem, but basically he really wants to prove that some iterations of the QIs is injective. And to do that, he has to prove that some QIs are injective, and he will show that the kernel of the QI is 0, but by the following theorem. So he reduces the Milnor conjecture to proving that some motivic cohomology group of some smooth variety, simplicial smooth variety, to be 0. And the geometry given by two results of Marcus Roth gives us vanishing of another motivic cohomology group. But he points out that you have an explicit cohomological operation, an iteration of QIs, which maps the one he wants to vanish to the one you know to vanish by the geometry. And you just want to prove that this composition is injective in some sense. So now you are back to the following theorem, Wygotsky. So K is characteristic 0. Take an integer like that, and Q be a quadratic, a projective quadratic of dimension 2 to the n minus 1. Let, so another notation, say tilde of Q be the cone or the cofiber of the morphism from C check Q, so the object over there, to the point. So this is a pointed object now. This one has no base point, but taking the cone, I give you a point. And as it is pointed object, I can talk about its reduced motivic homology. When you have a pointed object, the motivic homology of the point of spec K is a direct factor, a direct summand, canonical way, and the reduced motivic homology is the other direction. Okay. The homology of the reduced motivic homology of this object here with respect to Qi is 0 for I less or equal to L. So the Qi satisfies this equality, so it defines a derivation on the mod 2 motivic homology of any object. But for this particular object, when you take the reduced motivic homology, the homology with respect to this derivation is 0. So this gives you some information on the kernel of each Qi, discovered by the image of the previous Qis. And miraculously, in the area you want to study the Qis, the previous Qis start from 0. So this proves the required injectivity. So do I have time to sketch you? I could sketch you the proof for I equals 0 for the Bochstein, which is already which is very easy, and just say you where you need homotopy theory to do the general case. Proof for I equals 0. So you want to show that the Bochstein, which is derivation, homology on this gadget is 0. So it is really seen that the statement is equivalent to that the following morphism, motivic homology of C tilde of Q with mod 4 coefficients, multiplication by 2, is 0. Using the long exact sequence associated to the short exact sequence, Z mod 2, Z mod 4, Z mod 2, the statement for the Bochstein is equivalent to prove that this morphism is 0. This is quite elementary. So we want to prove that this morphism is 0. And so this theorem is a triviality if Q has a rational point, as I already mentioned. But if Q has no rational point, it certainly has a rational point with quadratic extension. So Q has a rational point in a field extension L of degree 2. So now you see this morphism as a multiplication by the degree of this extension, where Q has a rational point. And this is the main idea. As this is now multiplication by the degree of L over Q. And this using standard properties of transfers, in motivic homology, you can prove that multiplication by the degree of the extension is the composition of the following morphism. We can go from this one to motivic homology of the C tilde of Q extended to L. Just because as a smooth variety, Q cross spec L over spec K maps to Q. So you have a natural map of simplicial smooth variety from this object to this one. So by pulling back, you have this map here. So this is pull back map. And now you have a transfer morphism, because this morphism is finite étal morphism. And the composition is multiplication by the degree. Okay? But now, as Q has a rational point, which coefficient L, this gadget is equivalent to the point, and this group is 0. So we have proven that this composition is 0. And basically, the general case, I general, is uses the same strategy. I can just show you a few changes. So here I do not use any homotopy theory. It's just a property of motivic homology. Now I use homotopy theory there. So one, in the previous proof, motivic homology with U mod 4 coefficient appears as the fibers of the Bockstein. So as a cohomology theory in the category of smooth varieties, it is the fiber of the Bockstein, which is natural transformation like that. Now you just introduce for any I, this on N, a new cohomology theory, which is the fiber of the operation Qi. Okay, so you can do that. But here you have to go out from the triangulated category of mixed motives. This object is a generalized cohomology theory which does not exist in the triangulated category of mixed motives. It does exist in the stable homotopy category. So this is where you need to get out from mixed motives. For example, for I equal 1, this is in some sense the two-stage of the Postnikov tower of algebraic K-theory spectrum, so which is not this integral coefficient. So, and you see that the statement is equivalent to show that some obvious composition for C tilde Q star to is 0. So you can reformulate using the long exact sequence associated with these sequences to prove that such natural transformation applied to this object must be 0. And use the same strategy. The point is that here you use that Q as a rational point in a quadratic extension. The corresponding assertion for I is that Q admits a morphism from a quadric of dimension 2 to the I minus 1. You just take a subquadric of the correct dimension, and you have some kind of higher dimensional point here. And in the argument here, you have a commutative triangle here, which uses a given morphism instead of a transfer morphism, which only uses the fact that the phi i's are some kind of orientable generalized cohomology theory. So you have such a triangulated diagrams, and by the same remark as above, the fact that Q admits a morphism from here you have to extend this object to not to some field, but to Q cross Q prime of a spec K, where Q prime is the quadratic of dimension 2 to the I minus 1. And this object here is also contractible. And we have proven that. And the only remaining point is that the diagram is commutative if you put here multiplication by the fundamental class of the quadratic Q prime in some sense, general sense, and the fact that this is at least up to multiplication by, yes, this is in fact in the case of mod 2 coefficient, the fact that it is multiplication by what you want comes from properties of characteristic members of quadrics, which Marcus will talk about. So this is basically in the same spirit. Okay.
give us where in this category being constructed?
Well, I can explain it to you. I mean, this is a little bit technical, but
So,
I mean, you have to understand by which object two motivic homology is represented in the homotopy category. So you have to have some understanding on the Hallam-Maclaurin spaces, which represent motivic homology. And then we define explicit homology classes in the mod 2 homology classes of these guys. Okay, you define a morphism in the homotopy category, which defines the homology class.
so it's different from what I said. You use the term automobile, but what is the property you have used? Because this Hallam-Maclaurin space is rather complicated.
Well, more or less, it is also some kind of infinite symmetric product of a sphere. So, well, the sphere. Well, you can take a sphere, the smash product of P1 by itself, n times. Yes, but you can. Well, it suffices to look at the diagonal, because by stabilization you can always go on the diagonal.
Excuse me, the basic stuff in this sphere is not built on sphere, but in the closed category,
Yeah.
So really, it's different from which topologies do, like CW complex.
Not so different. I mean, it really looks like equivalent homotopy theory, for example. If you look at the mod 2 equivalent homotopy theory, you have the same kind of picture. If you look at P1 of C with the action by complex conjugation, this is the basic. This is really analogous to the situation.
I mean, he didn't really write up to us there, right? So you have something available?
Yeah, I do. Some notes, yeah. Yeah. I mean, it's very. The basic problems are not do not concern the construction, but rather the property of motivic homology. You have some property of motivic homology which are rather involved with algebraic cycle homology. But once you know that, essentially the construction is quite formal. So the difficulty is not in the homotopy part. It is the resolution of singularity, algebraic cycle homology. In the homotopy part is quite smooth. I mean, yeah. The basic problem is to compute motivic homology of P1 cross X for any smooth variety. This is not so formal, to know. So.
Could you say some more words about the connection between this theorem and the comparison theorem of adoption?
I could, but it couldn't involve much time. I mean, it's difficult. It's difficult. Maybe Marcus will.
Would escape from this question by saying that this is already in the Napoleon system.
Yeah.
When they were starting to look at the A2, they were reducing to show that for certain splitting varieties, certain quadrics, or then H1x K2 is well injected if you pass to algebra. Well, the mentioning of certain homology groups of numerals, and these are the starting. Well, Napoleon system was looking at K-homology groups, but we may interpret them as motivic homology groups, and these are the starting groups. What's the starting groups? So this is already the
Yeah. Technically, you have three parts. You have the motivic homology part to establish properties, which is in fact the most difficult part. And after you have a generalization of Merkel-Suslin approach, and you have to use also.
The approach of the system is just you enlarge your field to a very big field which has no parallel homology anymore in the image, for example in H2 or Hn. And you do it by joining just function fields of quadrics of parallel varieties. And then over such a big field, the theorem is trivial. You show both sides, homology theory and parallel homology are just zero. And so you just have to show that nothing happens if you do one step. And this is exactly this quadric is one of these representing this step.
Maybe you could say something in the next talk.
I want to talk to you then.
Yeah.
Let's have a tea.
Yeah.
You could, if you want to say a couple words about
For example, the sphere, the construction of the